Welcome students. I am Mrs. Anjali Nadgouda, Department of Chemistry, KLS Gupte PU College, Belagavi. In our last video, we have completed group number 13, that is boron family. In that, we have studied in detail the atomic properties as well as physical properties and chemical properties. So, today we will start our video with group number 14 from P block elements. The pictures which you are seeing on this first slide, that is diamond or the graphite, that is pencil or silica gel, these elements they come under group number 14, which we call it as carbon family. Let us start with the occurrence, how they occur in nature. So the elements which come under group 14 are carbon, silicon, germanium, tin and lead. Out of that, carbon is a typically non-metal and its abundance is very much higher in Earth's crust. It occurs in elemental form as well as in combined form, that is in free form as well as in combined form. In free form, it occurs as a diamond and graphite, and in combined form, it occurs as carbonates, bicarbonates, etc. It has one speciality, that is it exists in three isotopic forms. Means as carbon is having the allotropes, simultaneously carbon exists in isotopic forms also. So which are these three isotopic forms? Carbon 12, carbon 13 and carbon 14. Out of that, carbon 12 and carbon 13 are very stable form in nature, whereas C14 is the radioactive isotope, means which decay after some duration of time. And how much its duration? That is time to become half of the initial concentration. It is half-life period, and that is 5770 years. Means to reduce it to half of the initial concentration, it requires this much years, this much time duration, and this is called as half-life period. Radioactive element is measured in terms of its half-life period, and from that its stability is measured or calculated. Okay, now where it is used, this carbon 14, that is radioactive isotope, is very useful in dating. Dating means to find out the age of anything, especially if you want to calculate the age of the tree. So this C14 is used, and therefore it is called as carbon dating method. Even for any monuments or any things which are newly discovered, so that age of that is found out by using C14 isotope, and hence it is said as carbon C14 is used for dating. The second element in this group is silicon, which is second most abundant element. It occurs in the form of sand, that is silica. Is it? 27.7% by mass of silica is present on the Earth's crust. So it's a non-metal and it occurs in the form of silica and silicates. Silica means SiO2, silicates means SiO3. the third element in this group is germanium, which shows the behavior like metals as well as non-metals, which we call it as metalloid. So it occurs in very small amount, that is in traces. Next one is tin, which is again, so last two elements tin and lead are metals. So these are very stable metals and usually they are unreactive. They occurs in the form of compounds, which we call them as minerals. So tin occurs in the form of cassiterite, that is SnO2. Now tin, the word starts with tin, T, but the symbol is Sn because the original name is stannous, and from that it is, the symbol is given as Sn. Okay. The formula of cassiterite is SnO2. Now this also occurs in two common allotropes, that is two different physical forms. One is white tin and another one is grey tin. So white tin is available or it is present at room temperature, whereas grey tin is stable below 286.2 Kelvin. And the last element in this group is lead, that is, which is a metal, occurs as galena, that is PbS. Chemical name is lead sulfide, and from this lead sulfide even the silver is extracted. Okay, because this lead sulfide contains impurity as silver. Okay. So let us start now with electronic configuration. We have seen the elements, their occurrence and their metallic character. Now from this you have seen that the first two elements, that is carbon and silicon, are non-metal. Germanium is metalloid and tin and lead are metal. Means non-metallic character decreases down the group, whereas metallic character increases down the group. Let us see the electronic configuration. Here is a table which shows the atomic number and their electronic configuration. Okay. Now, in first element, that is carbon, to helium, that is 1s2, then 2s2, 2p2, right? Then silicon, atomic number 14, neon, that is atomic number 10, 1s2, 2s2, 2p6, then 3s2, 3p2. So you have observed that in valence shell there are 4 electrons which are present in s and p orbitals, right? So the general electronic configuration of this group is rare gas ns2 np2. We have seen for boron family it is ns2 np1. Is it? Now one more thing you can observe here, in carbon 2s2 2p2 is there, means there are no d orbitals present in this, whereas in silicon the outermost shell or the valence shell is third shell, which consists of 3d orbital, but it is not filled with any electrons, hence we are not writing. Okay, but third shell consists of d orbital, means from silicon to lead all the elements they consist of d orbitals, right? Further, from germanium to lead, these d orbitals are filled, which are completely filled, 3d10, 4d10 and 5d10 respectively, right? In lead one more orbital is filled, that is 4f14. So as there are number of electrons which are increasing in inner orbits, there are some changes in the physical properties, even in atomic properties, because these inner core electrons are very much in the heavier elements, that is from germanium to lead. Okay. So let us study the properties one by one. First one is atomic radii. In the classification of elements and periodicity in properties, in generally we have studied that down the group as atomic number increases, the size also increases, right? But here the increase in size, that is increase in covalent radius from carbon to silicon is large, whereas from silicon to lead is a very small increase. Though it is increasing, but the increase is very small, right? Now why it is again? Again it is due to presence of d orbitals and f orbitals, which are completely filled. Okay. So here one more factor which we have to take into consider, that is the shielding effect. So this shielding effect becomes, sometimes it becomes very poor, sometimes it becomes moderate, or sometimes it becomes very large. It depends on the element, right? Okay. Now based on atomic size, the one more property, that is ionization enthalpy, that is energy required to remove the outermost electron. Whenever if the one electron is removed and if the atom becomes stable, that atom has a tendency to lose the electron very easily. Whereas if the electron is actually required and we have to remove it, then it requires more energy, right? This is what trend we have already seen, that is when we go from left to right, ionization enthalpy always increases, whereas from top to bottom ionization enthalpy decreases. So when we compare this ionization energy of group 13 and group 14, obviously group 14 members ionization energy is higher than that of corresponding members in group 13. For example, when we study for boron and carbon, carbon is having higher ionization enthalpy compared to boron, like this. Okay. Now how it decreases down the group? Again, as we have seen, the size is increasing from carbon to silicon is large, therefore ionization enthalpy difference is also large. Means for carbon it is very high and for silicon it is very low. Okay. But after that, from silicon to tin, the ionization enthalpy decreases, but this decrease is very small. Okay. If you see that box or the table which is given in the textbook, you will come to know what are the values. Okay. Then what happens from tin to lead? Then tin to lead, little bit increase takes place in ionization enthalpy. Now why this is? Because of little increase in size as well as poor shielding effect of intervening d and f orbital. Intervening means inner core electrons which are present in d and f orbitals. So here the shielding effect is very poor. Okay. Means the outermost electron is not shielded properly by the inner core electrons. Means what? The outermost electron is more attracted towards the nucleus. Hence, the energy required to remove that electron is very large, or we can say very high energy. Okay. Next property, that is electronegativity. What is meant by electronegativity? It is the capacity to attract the shared pair of electrons in a molecule, right? So, in this group, the electronegativity decreases from top to bottom. But how this decreases? It's not continuous decrease. But from carbon to silicon, it decreases too much or it decreases very large. Whereas from silicon to lead, the electronegativity values remains almost same. Means there is no large difference in electronegativity. Okay, now why this happens? So due to small size, these elements are more electronegative than group 13 elements. And when we compare in group 14, carbon is the most electronegative element due to its small size compared to the other elements in the group. Okay, now let us see the physical property. These all four elements, that is carbon, silicon, germanium, tin and lead, all are solids. We have already seen non-metals, metalloids and metals, right? Out of that, tin and lead are soft metals with very low melting point. Okay. Melting point and boiling points of group 14 elements are higher than that of group 13 elements. Next one, let us see chemical properties. So chemical properties mainly depends on oxidation state, right? In last boron family we have seen it shows +3 and +1, right? Maximum is +3 and minimum is +1 oxidation state. That is group valency and 2 less than that of group valency. Here also the group valency is 4 because that is group oxidation state is +4. Why? Because there are 4 electrons in the outermost or valence shell, NS2, NP2, right? Okay, but along with that even +2 oxidation state is also there. Now for which elements? For germanium, tin and lead, means last 3 elements they show +2 oxidation state. Now what is one more speciality? Carbon. Yes, carbon is even showing the negative oxidation state whenever it is in the form of carbides. Okay. So tendency to show +2 oxidation state increases from germanium to lead. Now why it is? The reason is due to the inability of NS2 electrons of valence shell to participate in bonding. See, due to presence of number of inner core electrons, sometimes the NS2 electrons, they do not take part in bonding, and this we call it as inert pair effect. Means whenever they have to take part in bonding, obviously they have to unpair themselves. Unpair means what? They have to go away from each other, or they have to break their pair, is it? They have to become single. But these NS2 electrons are unable to become unpair, and this we call it as inert pair effect. And due to this inert pair effect, the last 3 elements they show +2 oxidation state. Now what are the other properties? Compounds in +4 oxidation state are generally covalent in nature. Now covalent means what? The compounds which are formed by sharing of electron pair, because they do not have the tendency, or they are having inability to donate the electrons or to accept the electrons, means they cannot form the ionic compounds, but they choose to form covalent compounds. Now why it is? Because to lose the electrons we require energy, and this energy is very high. So some of the first four ionization enthalpies is very high, and hence in +4 oxidation state the compounds are covalent in nature. Okay. Next one is tin forms compound in both oxidation state, that is in +2 and in +4 oxidation state. SnCl2 or SnCl4. In +2 oxidation state it acts as reducing agent. This property is for lead also. So lead also exists in +2 and +4 oxidation state. So out of that, +2 oxidation state is very much stable, and it acts as oxidizing agent. Okay. So what is meant by a reducing agent and oxidizing agent? This is already we have learned in the topic redox reaction. Okay. So the different types of nature and the variety of oxidation state we can find out in these p block elements. Now how it reacts with air, that is reactivity towards air. All the members when heated in oxygen form oxides. For example, carbon, let us see, carbon plus oxygen, we have two different products. One is carbon monoxide, another one is carbon dioxide. Is it? So like that, other elements also form the two types of oxides, that is monoxide and dioxide. Monoxide means the oxide which contains only one oxygen, and dioxide means the two oxygen atoms. Right? So the general equation is given here. 2E plus O2 when heated, remember heating is required to give EO or EO2, where E is an element of these group. So this is the general reaction for the group, remember, means any element you can put for E and then you can write the equation. Okay. Now SiO, that is silicon oxide, only exists at a very high temperature. Oxides in higher oxidation state of elements are generally more acidic than those in lower oxidation state. What does it mean? See here, in EO oxidation state, for example, EO, that is CO, carbon monoxide, oxidation state of carbon is +2, whereas in CO2, oxidation state is +4. Is it? So this one is lower oxidation state and this +4 is higher oxidation state. Now what is the general statement? In higher oxidation state of the elements, the oxides are more acidic, means CO2 is more acidic oxide compared to CO, that is carbon monoxide. This is what the meaning of the statement. Now these oxides are not similar, or they are all not acidic, okay, but they are showing different behavior. Like let us see in monoxides, carbon monoxide, germanium monoxide, or tin oxide, or lead oxide. Out of that, carbon monoxide is neutral, whereas germanium oxide is acidic, And tin oxide and lead oxide, they are amphoteric. Amphoteric means they behave like or they react with acid as well as base. Is it? Whereas in dioxides, the first three oxides, that is CO2, SiO2 and germanium oxide, these are acidic in nature because they are in higher oxidation state, and SnO2 and PbO2, these two are amphoteric in nature. See how variable properties are there in P block. Though they are in same group, though they are having the similar electronic configuration in their outermost shell, but still the properties are changing from element to element. This is due to the inner core electrons, that is the electrons which are filled in d and f orbitals. Then reactivity towards water. So carbon, silicon and germanium, they are not affected by water, whereas tin decomposes steam to form dioxide and dihydrogen gas. Means this reaction takes place with liberation of hydrogen gas. Okay. Now in this, Sn, that in reactant state, comes in the product as SnO2. So if you see here, Sn to SnO2 oxidation takes place. Means itself it acts as what? Reducing agent. Right? So to whom it is reducing? To water it is reducing. Now this water is in the form of what? Steam. So that's why while showing the equation we have written heating sign on the arrow. Okay. So steam is decomposed, means water is decomposed into what? Oxygen and hydrogen. By whom? By tin. Okay. So this is the special reaction. Now what happens to lead? Lead is unaffected by water because of protective oxide film formation. Means one layer is formed which does not show any action of water on that metal. Okay, means metal lead is itself protected by forming a cover. Okay. Next and the last chemical property, that is reactivity towards halogen. In group 13 we have studied they form EX3, is it? So here these group 14 elements, they are forming EX2 or EX4, that is dihalide or tetrahalide. So this is the general equation. E, that is solid element, plus X2, that is halogen, gives EX2 or EX4, where E is element of group 14 and X is fluorine, chlorine, bromine, iodine. Okay. Now, what are the special properties of these halogens or halides? So, except carbon, all other members react directly with halogen under suitable conditions to make halides. Means who is not reacting with directly with halogens? That is carbon is not reacting directly with halogens. Okay. It shows the reaction, no doubt. We have one compound, that is CCl4, carbon tetrachloride, but the conditions are different. Okay, it does not react directly with halogens. Okay, now these most of MX4 or EX4 are covalent in nature, means how they are forming? By sharing the electron pair. Here the two exceptions are there, that is SnF4, tin fluoride, tin tetrafluoride and lead tetrafluoride. These both are ionic in nature. Okay. Then PbI4 does not exist. So these are again exceptions. The two forms, that is Pb fluoride of tin and lead, are ionic, whereas PbI4 does not exist. Means lead does not react with iodine. Okay. Now why it does not react with iodine? Because PbI bond initially formed during the reaction does not release enough energy to unpair 6s2 electrons. That is, inert pair effect takes place and excite one of them to higher orbital to have 4 unpaired electrons. Means ns2 electron, that is 6s2 electron, does not get unpaired or does not become single to form the further bonds. Hence PbI4 does not exist. Okay. Then heavier elements, that is germanium to lead, they form halides of the type mx2. Means stability of EX4 decreases down the group, whereas stability of EX2 or mx2 increases down the group. Now one more property of these halogens, that is they undergo hydrolysis. This property we have already seen in group 13 elements also. Okay. So stability of dihalides increases down the group. This is just now we have seen EX2, right? Germanium to lead, they are forming dihalides. Considering the thermal and chemical stability, GeX4, germanium tetrahalide, is more stable than germanium dihalide, whereas in case of Pb it is reverse. So PbX2 is more stable than PbX4. Okay. Now when they are going undergo hydrolysis, that is when they react with water, they form the complexes. Why they why they are forming the complexes? Because they accept the electron pair, okay, from the donor species. Now here, which is the donor species? Water is the donor species, because in water oxygen is having two lone pair of electrons and it always try to give that lone pair of electrons, and hence it acts as electron donor. Now what is an exception? CCl4 is an exception. Means CCl4 does not undergo hydrolysis. Okay. Now due to presence of d orbital, they are ready to accept the pair of electrons from water. So here is an example of SiCl4, silicon tetrachloride. So the pair of electron from water is accepted by silicon and hence this bond is shifted. Means chlorine comes out with the pair of electron. That is, chlorine becomes negatively charged. Right? And hence chlorine is replaced by which bond? OH bond. Right? And this is how the hydrolysis takes place. So this is for one Cl bond. Like that, remaining all three, means togetherly total 4 bonds are formed with OH. Right? So this step is repeated 3 times and this is how SiOH4 is formed, that is called as silicic acid. Okay. SiO2 .xH2O, that is hydrated compound, is formed. This is how the hydrolysis takes place. So here we will stop it and let us see the remaining part of this topic in next video. Thank you. Students, please do the regular studies.